morning, so good afternoon, students. Okay, now continuing what I've studied in class, in the morning class, very few concepts, and all those concepts we'll try to apply them here. Now, on the outer side, you have 22 degrees centigrade, and H1 is given on inside as 80 degrees, 80 watt per meter Kelvin, and H2 is given outside as 10 watt per meter Kelvin, respectively. The walls of the room are also at 22 degrees centigrade. So what he's saying is here it is 22 degrees centigrade. It's 22 degrees centigrade. And then the outer surface of the tank is black, and the heat transfer between the outer surface, this outer surface is saying it is a black, and heat transfer between the outer surface of the tank and the surroundings is happening by natural convection, that is H, and radiation, that is H radiation is also present here. That's what he is saying. And the convection heat transfer coefficients at the inner and the outer surfaces of the tank are given as so and so. You have written it. Determine the rate of heat transfer to the ice, to the iced water in the tank. Okay, so he's asking you to find out the Q value. Simply, what is the Q value? He's asking you to find the amount of ice. M, he's asking amount of ice at 0 degrees centigrade melts during the 24-hour period. Okay, this we will see later. This let's see in the beginning. So what I have to do? I have to draw the resistance circuit appropriately. So let me take this resistance shape. So this is the first resistance. Then you will have one more resistance, and this particular resistance, this is due to the spherical tank, and you will have two resistances here, one due to the convection, the other due to the radiation. It's like this. So the resistance circuit will turn out to be of this kind here. Now here we have T infinity 1, which is 0 degrees centigrade. Here we have T infinity 2, which is 22 degrees centigrade. And this is R convection 1. This is R conduction. This is R radiation, and this is R convection 2. So our aim is to find out these resistances here appropriately. Once you can find out these resistances appropriately, you'll be in position to calculate the Q. So what is R convection 1 here? The R convection 1 is as usual 1 by H1A. That is 1 by the H1 value is given as 80, and the area here is pi by 4. No, it's not pi by 4 here. It is sphere here. So what you have to take is 4 pi R1 square you have to take. So what is R1? Is the R1 value given to you? It is given. The R1 value is 3 meter. The R1 is 3 meter by 2 will be giving you 1.5 meter. That is R1 value. So take that value and substitute it here. 1 by 80 into 4 pi into 1.5 square. So calculate this value. You'll get this value in Kelvin per watt. So next you move on to R conduction formula. What is the R conduction formula in case of a sphere? It is 1 by 4 pi k into 1 by R1 minus 1 by R2. Okay, take these values R1 and R2 values so that the whole value will be a positive value. So it is 1 by 4 pi. The K value of the spherical tank is given as 15 because it is a stainless steel. It is 15 watt per meter Kelvin is given, and then the R1 value just now we have taken it as 1.5, and now you should know what is R2 value. Okay, to get the R2 value, thickness is given in the question. R2 is equal to 1.5 is R1 plus the thickness is 2 centimeters. 2 into 10 to the power of minus 2. So this will give you R2 is equal to 1.52 meters. That will be R2. So 1.52. So R conduction is done. Then R radiation you have to find out. Before we go to R radiation, let's find out R convection 2. The R convection 2 is 1 by H2 into A. That is equal to 1 by the H2 value is given as 80 watt per meter square Kelvin in the question, and the area is 4 pi R2 square. So that will give you 1 by 80 into 4 pi into the R2 value is 1.52 square. So that will give you R convection 2 value in Kelvin per watt. And the next thing is R radiation is 1 by H radiation into A. So here, how do you find out the H radiation? That's the question. The H radiation is sigma into epsilon into T1 square plus T2 square into T1 plus T2. Okay. In the morning class, I have solved this, how to get this formula. So what is sigma value? Somebody tell me what is sigma value. It is a Stephen Boltzmann constant. Somebody respond, please.
Sir,
What is
H to 10. You wrote 80.
H2? I'm sorry. I'm sorry. This is 10. This is 10. H1 is 80. Correct. So what is sigma value?
5.67 into 10 to the power of minus.
5.67 into 10 to the power of minus 8 watt per meter square Kelvin power 4. What is the epsilon value? Epsilon value, let us take it as 1 because what is given is the outer surface is black. So the epsilon is equal to 1. That is the emissivity value. We can consider it as 1 because it is given that it is a black color on the outer surface. That is a clue for you. So you can take it as emissivity is equal to 1. What is the T1 value? What is the T1 value? Do you know what is the T1 value? It is not given in the question. Okay, the T1 value, where is this? This is see, this is 22, this is 1, and this is the other one. So you better write this in this nomenclature itself. So I'm writing it again here. It is T2 plus T infinity 2 square. Okay, because according to the nomenclature that we have said in our problem, it is like this. Okay, two temperatures. That's what matters. Okay. So is T2 given in question to you? Yeah. This T2 is given in
Sir,
question.
excuse me.
uh, mm,
Sir, Q due to radiation will be zero, right?
Q due to radiation will be zero. How can
Zero.
you say that?
Both the T1 and T2, I mean those 22 knows.
Because this is 22 degrees centigrade. This is also 22 degrees centigrade. That's why you're saying, right?
Yes, sir, I guess.
That is net rate of heat exchange is zero. You are right. Okay. Net rate of heat
Okay.
exchange is zero. But if you consider an individual body, the individual body, if it is having so and so temperature, it will emit radiation. You got the point?
Okay, sir.
So it will have the uh, heat transfer emission. Okay, at least it will have heat transfer being emitted. Okay, the radiation emitted, you can say it. All right. So what to do next? You have to take the T2 value and T1 value up, and then substitute the values here. The T2 value is 25, 22. See here what is written. The tank is located in a room, and this 22 is not for this one. Okay, I'm sorry. This 22 cannot be the case. The walls of the room means the outside. You can draw something like this. There is a room here. In that room, the temperature is 22 degrees centigrade. That's what he means. Okay, I understood it differently. This is a 22 degrees centigrade. See here, if this particular value is at 0 degrees centigrade and the K value of this one is 0.15 watt per meter Kelvin, this cannot be 22 degrees centigrade. Okay, this value cannot be 22 degrees centigrade. Okay, so you cannot take it as 22 degrees centigrade, and this value should be between 0 to 22. That we can say, but the T2 value will be most close towards this value. Okay, why I'm saying most close towards this value is because the thermal conductivity is 15. The thermal conductivity is 15. It's not 0.15. I have written 0.15 here. It is 15. So what, what I will do, I'll assume it to be 5. Okay, because it is not clear in the question. I am assuming so and so value, and this value is T2 is equal to 5 degrees centigrade. It's an assumption which you can make at your own convenience. Okay. Now, so what I'll do is I'll consider this T2 as 5 degrees centigrade. 5 plus 273 whole square plus the T2 is 22 plus 273 whole square into the T2 value is 5 plus 273 plus 22 plus 270. Okay, so that's how we got it. So tell me what is the H radiation value? What is the H radiation value? You calculate from this expression and tell me. Once you get this, you can get R radiation. Yeah. What is H radiation value? Did you calculate this? The H radiation value?
Five point three three.
5.34, you can take 5.34 watt per meter square Kelvin. So you take that value and substitute it here, 5.34 into A. The A value here is 4 pi R2 square, similar to your R convection 2. So this is 1 by 5.34 into 4 pi into the R2 value here is, what is that R2 value? 1.52, right? Square. You get the value in so and so Kelvin per watt. Now that you got R values on your resistance circuit, all R values are known to you in this resistance circuit. Now what you will do is you will go to the calculation of Q. Okay. If you want to go to the calculation of Q, Q is equal to delta T by R total. So that's how we get the Q value. But if you want R total, the R total will be the sum of R convection 1 plus R conduction plus R equivalent you will get here, because the resistance of radiation and convection 2 are in parallel. So for that, what you have to do is R equivalent you have to calculate using a parallel circuit. 1 by R equivalent is equal to R radiation plus 1 by R convection 2. So this is how we calculate this. So R equivalent is equal to R radiation into R convection 2 by R radiation plus R convection. Please tell me what are the values of this one. Resistance values. R convection 1, what is the value? Somebody please tell me what is this value?
4.42 into 10 to the power of minus 4.
4.42 into 10 to the power of minus 4. Good. R conduction value, you tell me?
4.65 into 10 power minus 4.
4.65 into 10 to the power of minus 4. Good. R convection to
0.0108.
R convection 2. No. It is. Did you take 10 here? I first have taken 80 here,
10
which
only.
is not. If
It's
you take 10,
3.44 into
3.
10 power minus
10 to the power of minus 4,
3. 3, 3, sir.
minus 3. Correct. Yeah. R radiation
6.45 into 10 power minus 3.
6.45 into 10 to the power of minus 3. So these are the values. Now we substitute those values into this equation here.
R total 2.73, 2 into 10 power minus 3.
We are directly telling our total value. No?
Yes, sir.
This was a problem. You are directly telling R total, right? Let me do this. It is 3.45 into 10 to the power of minus 3 into 6.45 into 10 to the power of minus 3, 3.45 into 10 to the power of minus 3 plus 6.45 into 10 to the power of minus 3. So what is this value? R equivalent. Somebody please calculate and tell me this value. Here, this value will be in Kelvin per watt. Then R total will be equal to 4.43. The value is 4.42. 42 into 10 to the power of minus 4 plus 4.65 into 10 to the power of minus 4 plus this value. What is this value? R equivalent.
Sir, 2.247 to 10 power of minus 3.
Here you are saying 2.247 into 10 to the power of minus 3. 2.247 into 10 to the power of minus 3. So now tell me what is R total?
2.73, 2 into 10 power minus 3.
2.73 into 10 to the power of minus 3 Kelvin per watt. Good. So now what you need is Q actually. The Q value is delta T by R total. The delta T is 0 degree centigrade is inside, that is ice, and outside is 22. So it is like 0 minus 22. For the positive effect, you can take it like 22 minus 0 also. Okay, only the direction matters here. Okay, heat flows from high temperature region to the low temperature region. That is in this direction. Okay, this is high temperature here. The 22 is high temperature and 0 is low temperature. So this is the direction. So I have to take this minus this if I have to get the positive value in that direction. So 22 minus 0. And the R total is 22.73 into 10 to the power of minus 3. Now somebody tell me what is the value of this Q.
Sir, how can we take 22, sir? There will be iron resistance, no, sir, due to convection.
Please repeat your question.
The outer temperature is 5 degrees, no, sir. 22 to 5 degrees, there will be convection resistance, no.
Say the 22 is on this side. Here is your T2 and here is your T1. Here you are considering 5 degrees centigrade. Okay. If you are considering only two resistances, R convection one, R conduction, you take 5 degrees, no problem. But you are considering R total. If you are considering R total, you have to take 0 minus 22. You got the point?
Yes, sir.
Is that clear? Yeah. Where we are. Yeah, Q value. Somebody please tell me what is the Q value.
Uh, 108.05 kilowatt.
Or not 8
Yes, sir.
No.
8058.6.
Yes, yes, sir.
8058.62 watts. So that's your Q value he's asking you to find. Okay, so this is one thing.
Degree.
And now see this T2 you have considered it as 5. Okay, that's an assumption anyways. But if you take it and cross check it now, again you will get that. Okay, so let me show that to you. So from the resistance circuit itself, as somebody has asked just now, let me take it and prove it for you once again so that it will be even more clear. So if you want to calculate the Q here, the Q will be like T1, or you can take like T infinity 2 minus T2. I am coming from this direction by R equivalent I will take. If this is the case now, see the R equivalent is influenced by your T2. So the T2 value you can get from this. So the T2 is equal to Q into R equivalent plus T2. So that will be the Q value is 80 something, we got 58.62. 8058.62, that is one thing. The R equivalent is what is R equivalent? It is 2.247. 2.247 in the kind of power of minus 3, and the T infinity 2 is 22. Okay, if you want T2, it should be minus, I guess. 2, yeah. Minus you will get here. You will get a minus here. 22 minus, you have to take all this. Somebody tell me what is the T2 value?
Sir, sir, it's approximately 4.
4 degrees centigrade. See, this is almost nearly equal to 5 degrees centigrade. So your assumption holds good. Okay, that's what the meaning of it. Okay, since you have considered some value which is not given in question, this is how you can cross check the assumed values, whether you have assumed in the proper direction or not. That's what the use of that. And his question B also here. The question B is, what is the amount? M he is asking. Okay, what is the amount of ice at 0 degrees centigrade that melts during 24-hour period? See, for this particular question, what you have to do is Q is equal to m dot into HFG formula you will take. This formula you will learn in your thermodynamics course. Q is equal to m dot HFG. This is what you should take. And then m dot he is asking, it is Q by HFG. The Q value just now we have found out 8058.62. That is your Q value. Do you know HFG value? You don't know. The HFG value you have to go to data book and get it. Okay, if you go to your data book in page number 152, I guess this value will be available to you, and that value is 333.7 kilojoule per kg. This value you will get for water or ice combination. Okay, that value you have to substitute it here, 333.7 This one is in kilojoule per second. This is in, sorry, this is in joule per second, right? This is not in kilojoule per second. This is in kilojoule per kg. This is kilojoule per, oh no, it is joule per second. It's watts, so it's joule per second. So what you have to do is you have to convert this value into uh, into kilojoules, and appropriately you have to take the 24-hour value also into it, and then convert it into the appropriate seconds. Okay, so if you do that, let me take out this from here, and then if I have to get this q here, let me write this as q dot or some different q. This q dot is equal to q into the time that you have to take. Okay, the time is 24 hours. This is 8058.62 into the time is 24 hours into 3600 seconds. So that this value will be in joules now. Okay. Somebody tell me what is this joule value? What is this value in joules? Kilojoules. Somebody confirm? Am I right? This kilojoule goes, and they will have the answer in kgs. What is the value? This 2079 kgs. That will be the quantity of ice that is there uh, inside that spherical tank in 24-hour period. Okay, if the atmospheric temperature is maintained at 22 degrees centigrade throughout, and this much 2079 kgs of ice will get melted because of the heat transfer from outside to the ice. Okay, that's what the point is here. So, anyways, the second part we will understand more when we make use of the data book that we will do more perfectly in your unit 4 for this HFG. That is especially in the condensation and boiling chapter. Right. So let me move forward to the next question. So if you have any questions regarding this question also, you can ask. Otherwise, I'll move to the next question. Here is how your question goes. Okay. Before this question, let me tell you a simple thing, that is critical radius of insulation for sphere. The critical radius of insulation for sphere RC is, for cylinder, somebody tell me what is the formula for cylinder?
K by H.
K by H for cylinder, but for sphere it is 2K by H. Okay, that is the only thing. So keep this in your mind clearly. And one more thing is the assignment that I gave you, in that also you add this. Okay. Here you add RC. For the slab, you will not have any value here, any formula here. Here the RC value for cylinder is K by H. K by H. And the RC value here is 2K by H. That one also you will add for cylinder speed. That will be of use to. Okay, let's move on to the next question. This is a question here. And for this question, there is a diagram also. Let me take the picture also. See, this is a I here. Okay. What he's asking you to do is consider this as I. If you consider this as I, treat I as a spherical system. Treat I as a spherical system and assume the system to be at steady state. And the convection heat transfer coefficient is unchanged with and without the contact lines in space. So what he is giving you is giving you a problem wherein you have an I, this is I, and for this I you have added the contact lens. Okay, that is the question basically. So, and he's saying that the heat transfer coefficient H naught is not varying with the contact lens and without the contact lens in place. The cornea and the lens cover 1/3 of spherical surface area. This 1/3 you remember clearly. Even if I remember, even if I forget, you ask me to take it appropriately. And the R1, R2, R3 values, these are R1, R2, R3 values. And the values are given for that. Temperature values are given for that. And the K1, H2, HI, all the values are given. And he's asking you to find the construct the thermal circuits, labeling all the potentials and flows for the systems, including the contact lens and including the contact lens. That is for the two cases. What he's asking is asking you to find the draw the thermal circuit. That's what he's asking. That is R values. You have to find the temperatures. You have to find and show it appropriately and determine the heat loss from the anterior chamber with and without the contact lens in place. So he's asking Q with contact lens, what is the value? Q without contact lens, what is the value he's asking? And discuss the implication of the result that we will do. Okay, so that's the question. So first thing is to draw the resistance circuit. Okay, let's draw the resistance circuit. If I draw the resistance circuit here, how many resistances I will get? Somebody tell me. See, all these problems are there in your Google Doc. You may refer to that Google Doc for the yeah. How many resistances?
4.
4 for with or without?
With the lens.
So here I have drawn 4 resistances, and these 4 resistances are for 4 4 corresponding anterior chamber, cornea, contact lens, and the outside atmosphere air. So here what I have is T infinity I, and here what I have is T infinity outer. And let me call this as T1. These are not required here, so I will not write it for now. So if you feel like writing, you can write it because he's asking you clearly what is the resistance circuit. You should write everything that is there here. Okay. For now, I will not write it. And the first one will be the resistance due to convection on inside of the eye. And the outer one will be convection due to outside of the eye. Okay. That is the atmosphere. And this is R due to the cornea. And this is the R due to contact lens. Okay. These are the resistances, and you have to find out the resistances. And what we are doing is we are doing it with Q with first, and this is the resistance for with the contact lens case. With the contact lens case, we are doing first. Perfect. We have to find out the resistances. The first one we do it, that is R convection on inside. R convection on inside is 1 by H A. So H on inside, is it given in question? H infinity I according to him. H infinity H I. H not H I according to him. It is given as 12 watt per meter square Kelvin. So substitute that 12 here. 1 by H is 12 and the area is 4 pi R1 square. So 1 by 12 into 4 pi into the R1 value we need is 10.2 mm. So the 10.2 into 10 to the power of minus 3 whole square. You'll get this value in so many Kelvin per watt. That is R convection in value. Then let me calculate R convection out value also. It is RHO and A. AIO is 1 by HO is given in the question as 6 watt per meter square Kelvin. Let me put that 6 here. 4 pi, and this is R3 square because we are considering it with the contact lens. This R3 should be considered. This R3 should be considered. So this is equal to 1 by 6 into 4 pi into the R3 is given in question as 16.5 mm. 16.5 into 10 to the power of minus 3 whole square. You'll get the value in so many Kelvin per watt. R convection in, R convection out are done. Let me go to the R. See, again, I did a mistake. I thought I will forget and I forgot it again. And this should be taken by 3 here, by 3 here, by 3 here, by 3 here. Why by 3? Because he is given the one third of the spherical surface area. And the whole area of the eye cannot have that contact with the atmosphere. Only the eye that is exposed to the atmosphere we are considering here. Okay, eye that is having the contact lens and eye that can be exposed to the atmosphere only we should consider, and it is only one third area of the whole sphere, so you cannot consider to be the complete sphere. Okay, so it should be by 3 everywhere. Take care of it. And R cornea, you have to take R cornea. Now it is a sphere, solid sphere. If that is the case, the R value is 1 by 4 pi k into 1 by R1 minus 1 by R2. This is the value, and 1 by 4 pi. The k is k1 here. The k1 value is given as 0.35 watt per meter Kelvin. Substitute that 0.35 here, 0.35 into 1 by R1 is 10.2 into 10 to the power of minus 3 minus 1 by R2 value is 12.7. 12.7 into 10 to the power of minus 3. So I'll get this value in so many Kelvin per watt. It is R cornea, and you need resistance value for contact lens. It is again 1 by 4 pi k 2 now, because it is a contact lens here. It is 1 by R2 minus 1 by R3. That is equal to 1 by 4 pi. The contact lens K value is 0.8. 0.8. So substitute that here, 0.8 into 1 by R2 value. What is the R2 value? It is 12.7 into 10 to the power minus 3 minus 1 by 16.5 into 10 to the power minus 3. You get this value in so many Kelvin per watt. Now we are done with all the resistances. Get the all resistances value here. What is our convection in value? Somebody please tell me. Yes, are you calculating? I want this value. This one. Yes, please tell me that value.
Sir, is it 180?
180, yeah.
191.21, sir.
191.21 Kelvin per watt. That's correct. How about the next one? R convection on the outside.
146.14.
146.14. Good. Cornea, R cornea.
2.8976. 2.89, sir.
2.89, huh?
Yes, sir.
No, I think. Yeah, again, we missed one thing here. It is area. Okay. So what you have to do is you have to take 3 into here. Why 3 into means? Because it is the one-third area that we are taking. Area will be in the denominator. Okay, by 3 if I take no, that will come into the numerator. That's why whatever the answer you got, into 3 you do and tell me.
8.69.
8.69 cornea you are telling, is it
Yes,
for
sir.
cornea?
Yes, sir.
Are you sure? I think it's not exact value. The value will be
52.56.
no. It's around
13.16.
13,
13.16.
13, 13.16 Kelvin per watt. Yeah.
Sir,
R
can we
with
consider
contact.
12.3 also?
Which one?
The same 13.16. Can we consider 12.3?
Approximately is okay.
Okay.
No, sir.
We'll try to do.
13.16 only.
13 and 12 are almost near. That's what he's asking. It's okay. That's what I'm trying. Our contact lens value
5.41.
5.41 Kelvin per watt. So these are the resistance values that you have got. And for this, you will get Q value also. So the Q value is delta T by R total. And delta T now will be the 37 that is prevailing out, that is prevailing within the eye. And the outside temperature is given as 37 is normal atmosphere, normal human body temperature. That's why 37 is taken here. And 21 is the normal atmosphere temperature, that is 21. 37 minus 21 by the R total. That is sum of all these resistances you have to take here. It is 191 point, what is that value? 191.21 plus 146.14 plus 13.16 plus 5.41. Tell me what is this keyword. And I mind you, this is Q with the contact lens. What is this Q value? Somebody calculate and tell me.
0.044.
0.044. Few more numbers, few more decimals.
9539.
95 watts. That is the Q with the contact lens. Okay. Now we have to calculate it without contact lens. For that, we have to draw the resistance circuit again. So I'm taking the resistance circuit, and in this resistance circuit, now I don't have the contact lens. So what I'll do is I'll remove this part. And now I'll write this as R convection 2. And this will be my T infinity outer, which is equal to 22. Okay, so this is 37 degrees centigrade. Now, tell me what is R convection in this case. So I'm going to the second case. The second case is without contact lens. This is the case I'm considering. So this value will be the same for both the cases. So you need not do it again. It is 191 point. What is that? 16. 191.21. 21 Kelvin per watt. Next one is R cornea. And this R cornea will also won't vary. Okay, it is what is the value? 146. No. It is 13.16. It is 13.16 Kelvin per watt. And now R convection outside will vary here. Okay, because it is 1 by H A. This is H outer. This 1 by H outer is given as 6 in the question, and the area is 4 pi R2 square now. Previously it was R3 square. Because there is a contact lens, we have to consider the radius of the contact lens. Now there is no contact lens, so R2 has to be considered here. It is 1 by
Again,
6 into
area by divided by 3 is no, sir. So,
again area divided by 3.
yeah, yes, sir.
Thank you. I'll always forget this. Thank you for reminding me. Yeah, by 3, and the R2 value is 12.7 mm. So 12.7 into 10 to the power of minus 3 meters whole square. We will have. Tell me what is this value in Kelvin per watt?
246.69.
246.69 Kelvin per watt. Thank you. So now you have to get the Q value with, oh sorry, without, well, we have done for without contact lens. It is delta T by R total. So that is equal to 37 minus 22 by sum of all the resistances that you have here. It is 191.21, 191.21 plus 13.16 plus 246.69. So, so tell me what is this value?
0.035.
0.0355 fiber. Okay, watts. So that is a value. Now, this I will write in milliwatts, and this will turn out to be 44.9 milliwatts. Okay. And here also I will take it as milliwatts. This will give you 35.5 milliwatts. So Q width is equal to 44.9 milliwatts. Q without is equal to 35.5 milliwatts. Okay. So from this, what can you understand? Okay. C, question number C. You see, he's asking, discuss the implication of your result. He is saying, what is the implication of this result? What happens when you have a contact lens? Okay. So question C answer will be, contact lens is increasing the heat transfer through the eye for the thickness of contact lens considered in the problem. So, so whatever the thickness that is considered in this particular problem, if that is the thickness that you are going to have on your eye for your contact lens, then the heat transfer will increase. Okay, that's what the thing is. Since it increases, what happens? The human will feel the irritation. Okay, whatever the irritation is there, it is because of the increase in heat transfer. Okay, that's the point. And one more thing is, let me do R critical here. The critical radius of insulation, if I take it here, it is 2K by H, isn't it? So the K value of the contact lens is given as 0.8 here, and the H value on the outer side is given as 6. So calculate and tell me this value. 2 into 0.8. What?
0.26.
0.26 meters, that is 26 centimeters. See, see, till 26 centimeters. See, if this is the case now, what is the thickness here? The radius here, it is 16.5 mm. That is 1.6 centimeters. This is just 1.6. This is just 1.6 centimeters. And if you have critical radius of insulation, what will be this thickness? this much it is there, and this RC will be equal to 26 centimeters. Imagine the contact lens with 26 centimeters, which is not feasible in practical reality. Okay, but the point I want to draw here is till 26 it is going to increase. Okay, critical radius of insulation is a radius where the heat transfer is maximum. So till 26 centimeters, your radius will, sorry, your heat transfer will keep increasing. So the heat transfer will increase. R critical, let me put it as small r. R critical is 26 centimeters. That is 1.6 centimeters. R critical is 26 centimeters, which is not feasible in reality. In reality, you cannot have a 26 centimeter thick, 26 centimeter radius contact lens. That is not possible. Okay, and till then, till 26 centimeters, heat transfer will keep increasing. So, if you have to design contact lens such that it has less irritation, that is less heat transfer will be possible if the least possible radius or thickness is designed for the contact lens. Is it clear? See, what I'm trying to draw out of this is when somebody wears this contact lens, heat transfer is going to increase for sure. When heat transfer is increasing, what you are left out is you have to choose a thickness which is the least possible, because least possible will have least possible heat transfer. Okay, that's what the point that I would like to draw from this particular thing. Okay, so if you have any doubts in this, you can ask me. No doubts? I hope it gave you an idea of how a contact lens works and how the heat transfer concept, especially this spherical coordinate system, there is a sphere problem, can be understood from a eye problem. Okay, somebody was asking me in the beginning classes that what is the use of the spherical coordinate system and what is the use of the sphere and all these questions they have asked me. This is one particular use of the spherical coordinate system. I hope it's clear. If you have any questions, please do ask, or otherwise, let's move to the next question. I hope it's clear, and I'm moving on to the next question. There it is. All these questions are updated in your Google Doc. Please refer to your Google Doc for these questions, and you may copy it into your notes also. All of them are available there. All right. So this is one more question based on sphere. Here what is given is a hollow sphere is given. It is made up of two materials. First with so and so K. Let me first draw the first one. That is first thickness. Let me draw. And then there is second one. So I will draw for the second one also. Let me put it. That's the second one, and the first one you can see. And since there are three here, you will have three radiuses coming into the play. The R1 will be equal to the 10 centimeters by 2. That is 5 centimeters. And the outer diameter of the first one is 30 centimeters. So R2 will be 30 centimeter by 2. That is 15 centimeter. And there is a third layer with 40 centimeter outer dia. So 40 centimeter by 2 is 20 centimeter. So this is the value is given. In between these two, you will have K. Let me call it as K1, which is equal to the 70 watt per meter Kelvin. In between these two, I have K2, which is equal to the 15 watt per meter Kelvin. This is the value is given. And the inside and outside temperatures are given as the inside is 300, the outside is 30. Respectively, estimate the rate of heat flow through the sphere, assuming perfect contact between the materials. Also, calculate the critical radius for outer material. Okay, so if you have to do this, Q, you have to find it, and RC, you have to find it. That's the thing. And I have to take the resistance shape here, take the resistance shape, and how many resistances you will have here? Basically, you have only two resistances because only two materials are there. The temperatures are given for only two materials. So obviously, you will have two materials here. And this one is 300 degrees centigrade. This one is 30 degrees centigrade. This is R conduction one. This is also R conduction. This is a simple problem. Nothing great in this one. Okay. Okay. Uh, so this is the heat transfer direction, high temperature region to the low temperature region. If you want to write Q here, Q is equal to the delta T by R total. You have to do. First one is R conduction one, which is equal to 1 by 4 pi K into 1 by R1 minus 1 by R2. That is equal to 1 by 4 pi. The K value for the first one is given as 70 into 1 by R1 value is given as 5 centimeters. So you put 5 into 10 to the power of minus 2 here. And then the R2 value is given as 15 centimeters. So you put 15 into 10 to the power of minus 2. You'll get the R conduction 1 value here in so many Kelvin per watt. If you're done with R conduction 1, move to R conduction 2. It is 1 by 4 pi 1 by 4 pi K2. This is K1. is 1 by R2 minus 1 by R3. That is equal to 1 by 4 pi. And the K value for the outer thing is given as K2 is 15. 15 into 1 by 15 into 10 to the power of minus 2 minus 1 by 20. Yeah, 20 into 10 to the power of minus 2. So tell me this value in Kelvin per watt. Also this value in Kelvin per watt. Yes, please tell me.
So our conduction one, I guess it is 0.0151.
0.0151 Kelvin per watt. I'm taking you for granted.
And our
Others cross
conduction
check it.
and our conduction two is 8.841 to 10 power of minus 3.
Kelvin per watt. Okay. So now what I need is Q. Q is 300 minus 30 by the sum of these resistances. It is 0.0151 plus 8.84 into 10 to the power of minus 3. Tell me what is this Q value?
11273.48.
11273.48 watts. That is equal to 11.273 kilowatt. Okay, that's the Q value is asking you to find. You're done with it. And the next value is asking you to find out is the critical radius of insulation. Critical radius of insulation is not calling here, is simply calling it R critical for the outer material. So what I have to take 2K by H because it's a sphere here. The K value we have to take it for the second material because he's asking you for the second material because we can have it only for the second material. Is the point there. The K2 value is 15. What is the K2 value? It is 15 given in question. And the H value is it given in question? H value is not given in question. Consider that H is equal to 10 watt per meter square Kelvin. So we put the 10 here. That is equal to 30 by 10. That is 3 meters. Okay, R critical is 3 meters, which is a huge value. Actually, 3 meters means if you compare it with 20 centimeters, till 3 meters, it's going to increase. If it's 3 meters, the Q will be max. Okay, is it clear? Do you have any questions at this level? Yeah, I hope I'm clear. Let me take you to your syllabus now. Where is your syllabus? See, this is your syllabus. And in this syllabus, you can see first three are done. Okay, the composite slab is done, and then composite cylinder is done, sphere is done, overall heat transfer coefficient, electrical energy, critical radius of insulation. Till here we have completed. Okay, these three concepts are done. These concepts are still left out in unit 2, so we have to move little faster. Since this is online class, I'm going little slower only. Actually, I thought of going very fast, but I don't think that will be helping you. That's why I'm going slower. But the remaining, concepts, the variable thermal conductivity, the heat source, and this fins and transient, all these things, what I will do is I will try to reduce number of solved examples so that we can go little faster. And my request is all of you try to solve the problems on your own. That will be of help to you. If you don't do that, you cannot actually learn the subject. That's why I saw a lot of solid examples within the class that will help you understand the practical aspect of the problem with more clarity. So that's why I use a lot of solid examples and help you understand the concept and its application in reality. So I hope I'm clear with that. And that's all I have from my side.